Okay, hello again. We are ready for our next presentation. Zheng, the VP of Global Risk Analytics and Innovation Lead at HSBC, has extensive quantitative model development and deployment experience. His team is focused on developing AI capability and capacity, engaging with cross-function stakeholders to identify business opportunities and drive better business decisions through end-to-end analytical solutions. Formerly, he worked in decision management at Barclays. He holds a PhD co-major in applied mathematics and statistics from Iowa State University and a BSc in mathematics from University of Science and Technology of China. Please welcome Zheng.
Thank you. Can you hear me well? Yeah. It's an honor to hear, excited to present what we have done in stress testing that we developed some Ensemble models because we're trying to, get in the wave of AI and to see how that can be adopted in the financial service area, specifically under regulators' scrutinies. I'm pretty sure you have learned a lot of math in the previous sessions. So let me just give you, and you have learned a lot of definition between machine learning and AI. And this is a kind of a comic way to show that I'm in the right room to present to you. It's about artificial intelligence. But it is, in principle, statistics, right? You put a frame on it, and it becomes machine learning. You present to a bunch of audience, it's AI, right? But in principle, it's mathematics and statistics. So today's talk, so in CCAR stress testing, we developed an Ensemble approach, which mixed sequential model, you will see a traditional model, gradient boosting tree, you heard a lot in those 2 days, and the rating migration to predict the future term structure of corporate default risk. So first, I should give you a little bit of background of the history of HSBC. So we founded about more than 150 years ago. We survived through World War I, World War II. We helped reconstruct the Hong Kong economy, and we expand across the entire, Earth. So we continue evolving and continue innovate until today. So this is from our last year annual report. We actually have about a 2.5 trillion total asset, about a 54 billion total revenue. Our footprint is across globally. There are, a little bit shy of 4,000 offices across 67 countries. A lot of shareholders, even in more countries, 130 countries. And we have a little bit shy of 40 million customers, and also a lot of employees. So we have large presence across Europe, Asia, Americans. Sometimes we call ourselves global local banks, right? So that's a current footprint. Then this slide, we talk about our line of business and the range of product and service. So we have major 4 line of business. We have commercial banking, global banking and market, retail banking and wealth management, and the global private banking. And our product is crossing liability-driven, asset-driven, and fee-based. We actually have a really huge portfolio. A large portion is on credit and lending. So that's actually today's focus for this project. So what is CCAR and the stress testing? So CCAR is a short name for Comprehensive Capital Analysis and Review. So it's a United States, so US-specific regulatory framework that introduced by the Federal Reserve to assess and regulate and supervise those bank holding companies, so including large banks and financial institutions. They call it BHCs. And then the core part of this program is assessing whether the BHCs possess adequate capital, and then the capital structure is stable given different scenarios, stress testing scenarios, and then the consequences of planned capital distributions. So if you look at the cartoon that the bank is on the treadmill and being tested through all kinds of tests. You run 10 miles per hour, right? You run 12 miles per hour. Will you brake, right? Do you need a brake? So that kind of thing. So there are different scenarios. So this is a kind of overview of CCAR, but what does it mean quantitatively? So stress testing is forward-looking on quantitative basis. So there are 3 scenarios published by Federal Reserve. Is a baseline, adverse, and a severely adverse. As you can see from the name, meaning its baseline is more like a benign scenarios, kind of like a BAU, business as usual. And adverse is a little bit worse than baseline, and severely adverse, that's the worst. That's kind of mimicking the downturn, if you wish. But every year, you have different scenarios, different theme, right, by the Fed. And what we need to do is we need to take all those scenarios and determine the stability of the bank that in such scenario, right? For example, severely adverse, essentially that's an economic crisis. See if that, beyond those normal operating capacities, that do we have stable or to have sufficient capital to absorb any loss that under those scenarios. And for example, that you can see what happened if unemployment rate raised to, for example, 10% or 15%, GDP fell, equity market crash. What if all your instruments in the bank that terminate their contract in the next 2 years, right? So under those scenarios, what is the loss could be for the bank, right? And then we would need to assess whether we have sufficient capital to absorb that. So this gives you some idea of how those scenarios looks like. This is coming from 2018 CCAR scenarios. If you read it, so there are 6 variables that I just picking from the CCAR scenarios. The black line is a historical actual, right? And let me point it. So the black line, those are historical scenarios. And then the colored line are the future scenarios or hypothetical scenarios published by Federal Reserve. So there's 3 ones, right? Blue is the baseline, and orange is the adverse, and the red one is the severely adverse. So you can see the magnitude, right? The severities that increase. And also you can see that the peak of those, scenarios across different, variables or drivers, if you wish, that they have different severities, right? Sometimes they mimic the downturn. Sometimes they are much worse than the downturn, right? And sometimes they don't recover at all, right? So different patterns you can observe from different drivers. So what does that mean to us? So here come to the problem and the challenges that I want to walk you through, that those challenges we have and how we came up with this approach as a challenger model. And what's a lesson learned that is through the process by applying the machine learning and the AI models. Right? So the problem is that we want to predict the probability of default term structure for corporate customer under those 3 scenarios. The data inputs are customer informations, so including historical performance, right? In history, we know how the customer perform, how the corporate customer perform, whether they default or not, right? What's their rating looks like at each time point in the history, right? Which sector, industry sector they belong to, and which business they belong to, right? They might be corporate customers, CMB, commercial banking, they might be GBM, global banking, right? and the financial ratios, etc. So all the characteristics associated with the corporate. And the next one will be the macroeconomic variables. So those are very important that for us to build a relationship between the performance against the scenarios we saw before, the black line in the last slides. And the output will be default probability. And the challenge is, there are three main challenges: the variable dependency, and the scenario dependency, and the methodology dependency. I will walk you through one by one. So first, I want to quote the Nobel Prize. I think this quote is more than a century ago, but it's saying, prediction is very difficult, especially about the future. And I believe that still applies nowadays, right? Give a simple, because I know this mathematical form is really simple, but just give you an idea what's the component going to the prediction is you have a bunch of, we call it independent variables, x, right? And we have a target variable, which is y. And historically, you observe all those things. But you want to build some kind of relationship between those two that hopefully could establish a forecasting rules that you can piggyback that the movement of y by the set of quantity x, right? So this is we want to establish. But why this become a challenge, right? So first, the challenge is the variable dependency. So I guess this is a universal problems for data scientists, that you want to do variable selections for any data sciences problems, right? So we will do feature engineering and selections. There are main four categories that really specific to the CCAR stress testing: data availability and relevancy. So this is because that when we sourcing the data source, sometimes we're sourcing internally and externally. If you want to bring external data into our internal portfolios, you want to look at whether the data is available and whether the data are relevant, right? For example, if we want to bring financial ratios, right? A lot of times we want to do a fuzzy match, right? Because different names will pop up between our internal system and external system, right? Moody or S&P. So some algorithms can be applied there to bring informations, but we also need to be cautious about the relevance. The second one is variable stability and the significance. So this is purely from empirical perspective that when you build a model, that we want to make sure that the variable is significant and stable. And the third one, the fourth one, is actually very important for stress testing practice, that we want to make sure that this is what variable we choose have economic and business intuitions, because those models will be reviewed by business stakeholders, senior management, regulators. So that's why the fourth point, the regulatory feedback, internal feedback actually will drive a lot of portion of variable selections, right? So then the next one, I will just build some toy models, toy portfolios, that to show you that why this dependence exists. This actually just shows you three variables versus the default rate, right? Historically, just histograms cross macro variable 1, 2, 3, and the default rate, and the scatter plot associated with the lowest fit, and the correlations. But we want to build a model, three different models between default rate and those micro variables. And then we want to compare what's the performance looks like. So we use the same methodology. It's a toy model, right? Use a logistic regression. And each X will be used in three models, right? One model, each one variable. And this is how it looks like. The blue line, solid line in the graph, the blue line, solid line is actual default rate, right? And the three models is built by those. Each model will use just one driver that from the previous slides. That the back testing looks like this. One by the Model 1 is orange line, and the Model 2 is the green line, and the Model 3 is the red line. It looks quite, relatively okay when we're back testing, right? They all capture historical peak, which is around 2008, 2009 downturn, right? This is the purpose we do stress testing. We want to make sure that when crisis comes, the model will generate sufficient, will capture the peak or capture the loss. So it looks like okay. But we need to compare how those prediction under severely adverse scenarios, right? So that part, the question mark, we don't know. So we want to see. So this is the second challenge related to the variable dependency. This is also scenario dependency, right? So you can see the prediction is quite different across those three models. In the backtesting, the Model 1 has a peak over Model 3 and over Model 2. But in the forecasting, the order was totally switched, right? So Model 2 is almost double the peak, right? If you look at the green line versus the red line, it's actually almost doubled in terms of default rate. What does that mean for the bank? If you look at the credit lending portfolio, that means if your PD doubled and your LGD and the EAD stay the same, meaning you control everything else, you have a double your loss, right? So I don't think a bank has, we're not in the stage to tolerate that kind of, variabilities. So how do we do? So this is, so the second challenge is the scenario dependency. The reason why that we have such, range of predictions is simply driven by the variable itself, right? The variable is selected into the model that in the scenario, they behave differently. For example, the green one actually used the variable here that in the Fed scenarios, it's doubled the historical downturn, in the magnitude. So that's why the whole model prediction doubled, right? But here comes the best part. Our model is developed before the scenario released, right? And even I would say the model is developed and then being reviewed by independent model review, and then the scenario will be published, right? So you don't have time when scenario published and then you say, oh, shoot, my prediction is really high. Let's go change the model. So that will create a crisis within the bank. So what do we do? The methodology dependency. Keep that in mind, but I want to show you the third challenge. So first, still the famous quote from George Box, all models are wrong, but some are useful. And I want to show you this animation, simply that if you look at it, the X, Y, right, you look at it, they're simple statistics, right? You just second order moment up to second. Your mean, standard deviation, correlation, pretty much the same, but the different patterns showed up, right? So how to mining those patterns, even the dinosaurs. So how to mining those patterns, it's really about how you choose different methodologies, right? You choose different methodologies, you choose linear regression, you only capture correlation is about 0, you don't capture anything, right? So this shows that we probably want to go beyond and test what the AI and machine learning, those more advanced techniques can bring into the table, can improve the model performance. So that's what we did. We actually took different approaches for these problems, parametric approach, the logistic sequential approach, because it's a classification question, first of all. A non-parametric approach, we have random forest, XGBoost, artificial neural networks. And we end up building different classifiers based on those methodologies, and Ensemble based on the scenarios. And I will walk you through why we do that. The first step is clustering analysis. So for standardization, that's a key pre-processing step, right? Because you want to make sure that any correlations you want to run as a metric, that you want to standardize it, right? Or a principal component that I will show later. And then we did the time series clustering based on the shape of the series and using correlation as metric. So that will give us some sense of how those micro drivers can be clustered into different groups, right? And then the second is the way that we want to develop, construct an indicator or driver to overcome the dependency of the variable and the dependency of the scenario, the first two challenges. We use a principal component analysis. So once we have a set of variables that are from clustering, and we run a principal component, typically for principal component, you want to avoid the correlation, right? You don't want the really highly correlated variable to go into your raw variables and run a PCA, right? But here, actually, we don't mind that those, because we know that the economic variables are correlated. And we run a PCA is we want first extract important information, and the second, we want to reduce the dimensionality, and then still it's intuitive, right? Because talk about the PCA, if the little bit of brainstorm is not a brainstorm test, is if you think about two uncorrelated normal distribution, if you put on the scatter plot, it should probably give you a circle, right? And you add one more dimension, which is identical to one of the variables exactly, put it onto another dimension, so the circle will become an ellipse, right? But it will have higher contribution in terms of variance. So here, we want to capture that. We want to make sure that the information we extract would represent by the different microdrivers in the economic system, right? So that's how we did it. We have pre-selected 5 variables from the clustering analysis. And then we look at those variables which kind of correlated with our default portfolios. Right? And then we extract the principal component, especially the first one that captures the majority of the variance. So that's how the solid red line looks like for the first principle. Right? So this is with the historical actual scenarios that we extract this driver. We call it an economic indicator. And then we want to see how this looks like in the scenarios. Right? So still those 5 variables. Then once we go into PCA, then we extract the first component, we will see, oh, okay, this is how the historical looks like, and this is how the scenario looks like. Now you can see that this one actually is combine those 1, 2, 3, 4, 5 that could, the major kind of benefit is balance out the impact from individual microdrivers, right? You see this one is almost double, right? Or this one is a little bit over, but not that, severe as the second one, but the principal component kind of balanced those out. And also, using this as a driver, that you include all kinds of micro informations that in your model. So that's the principal component. And then once we, yes?
On the previous slide,
yeah.
When you say PCA, the economic indicator from the first component is intuitive.
Yeah.
Can you elaborate exactly what you mean by that?
Okay, so intuitive meaning, for example, if you look at it here, the peak of the principal component is the peak at almost 2008, 2009, right? So that's a downturn, meaning when downturn come, this principal component actually is severe, right? Going to the extreme, while in a benign economic environment, it's kind of a stable in the 0 kind of a range. Yes?
Have you looked at ALS, partial least squares?
The question is, have we tested PRS? Yes, we did test. But I think the PRS is you have more variables. But this one, we did some tweak at the beginning. We're not throwing all the variables in there. We just pre-select those correlated with our portfolio, and then to make sure. Because in PRS, you have less control in terms of which variable go into, right? And also the coefficient or the sign corresponding to each driver. You might have unintuitive signs, meaning if the GDP come in, supposedly, if your GDP going down, then your default rate is supposed to going up, right? So your sign should be negative. But the PRS might not give that.
With PLS, you're going to explore the covariance between X and Y as opposed to just the total variation of X.
But here is purely from X perspective. There's nothing to do with Y, right?
So this is only by accident that the PC1 is, like you have some meaning for the PC1 because the principal components are like a linear combination of whatever input you might have given, right? And in some cases, the linear combination may just be like one of those like initial variables that you entered. So, but if this was actually more like a linear combination, not just as like one of the input variables, it may not be meaningful at all, right?
So the question is whether this construction is by accident to be this way. So
Even that you get and it's meaningful as well. Like you can actually explain it in terms of like the economy going down and it's actually going up. If you probably carried out this PC analysis on some other data set, the PC one may not be explainable, right?
yeah, that's why there's a pre-processing step for this. I'm not just throwing all thousands of micros in there and find the first principal component. I'm find those ones that are correlated with my default portfolio and then extract, right? Because those PCA is constructed from those 5 drivers, 5 main drivers.
But if they're highly correlated, then the drivers would also be correlated. And PCA would actually try to orthogonalize them. And then in the end, you would have some kind of like a linear combination of the initial drivers. So you're probably less likely that the PC1 would actually be like meaningful to any of the initial drivers.
Actually, no. The reason being, first of all, those drivers, single drivers 1 to 5, is not that highly correlated. The correlation is like a 70%-ish, right? And the second is that's the purpose of constructing these drivers, right? If you think about, if I want to put those 5 variables into any logistic regression, you probably end up choosing one, right? The other will become insignificant. Then it will become the variable and the scenario dependency, right? Before that you will have that spike, right? But with this construction, that the PCA will balance out the spurious. And also, I can introduce those 5 variables, right, into, but I understand that so first, those extraction or linear combination stay the same in the forecasting, right? It won't change. That's a limitation. So that's why we have a sequential to capture the remainder kind of sensitivity across different segments, right? But for this is supposed to capture the main kind of economic drives, right? So I can tell you that, for example, some are unemployment rate, some are GDP, some are housing price, right? So those are the main drivers, right, for the economic. But I'm happy to walk through some details after. So going back to the slides, that the first methodology, more traditional, is we use a sequential GRM. So this framework is used to run a model against residual for given factors. So here, once we constructed the PCA, right, so we saw that as the main driver for the economy, then we use that as the first step. So sequential framework is basically to tear down a complicated modeling process to steps, right? And then the benefits would be it will identify the significance of adding new variables or interactions specifically. So for us, so the first step, we use that piece, the first principal component as the main effect, and to capture the main, forecasting or the correlation between our default and the economic indicators. And the second step, we'll model the interaction terms, the meaning if there are any residues that we did not capture or sensitivity that showed up between in our different segments, then we capture through that. Right? So in this way, actually the linear combination of those drivers is not holding the same in the forecasting period because I will introduce the interaction terms, so effectively it will change, so the correlations. The second method is the machine learning method, because we are here in the AI conference. We actually tested different methodology, random forest, gradient boosting machine, ANN. So after the testing, we end up choosing gradient boosting. I will tell you why. So here is just basically some high-level summary why we go from single trees to random forest to boosting. And the benefit of boosting is by training those models sequentially, you reduce both your bias and the variance. Right? Once we train the model, the interpretability is actually very important. That we have to tell our stakeholders, business stakeholders, they are not a quant, to understand how the model perform, right? Why, and also the regulators, they want interpretabilities, how you interpret those models. There are many different methods to interpret a model. Feature importance, partial dependency plots, IC, ALE, global local surrogate models, Sharpley's that you heard in the yesterday and today. Right? Those are different methods. And for gradient boosting, because it's a tree-based method, you actually can output different trees, right, to see how those models perform. And also you can see the entire tree in a cohesive ways, right? You project and you see how those breaks look like. So those actually help, that are based on our experience, to tell the business and the regulators how those model works. But those feature importance as PDP, those are definitely important. I will show you later why those are important. So let's now look at the model performance, specifically for the machine learning models. We apply the cross-validation. We apply the regularization, subsampling. We validate the hold out the sample. Looks good, right? Everything looks fine. But look at the back testing. The blue line is the actual, and the red line is the model prediction, right? It's really close. Looks too good to be true, right? So now we need to diagnose and understand the model. So first we do is a partial dependency. So partial dependency is reveal the relationship between your predictors and your target in the marginal effective ways, right? So there are some limitations with PDP, but I don't think we want to go to that detail, but it definitely help that you want to check this. So look at the partial dependency plot and tell me that what do you see some abnormalities. So the X is actually housing price index. And the Y is the prediction generated by the model, right? When you control all the other effects, right? So supposedly when HPI goes down, you're supposed to have higher default rate, right? And then when HPI, meaning housing market appreciate it, then you're supposed to have a lower default rate, right? So the thing that we want to look at is here. We know that when housing market crash, but why the default rate actually going down, then this stage, right? Because once it's going to this area, in terms of X, it's in this level for the Y, but suddenly it dropped, right? And also those local nuances, right? Why that happen? And then the second one is the predicted stability or sensitivity analysis. Essentially, we stress the model on the individual variables that, while keeping other variables unchanged. So the shock is by 1 standard deviation or 2 standard deviation. And the goal is to analyze whether the model generates reasonable results under those scenarios. So now actually I want you to focus on this area. So the blue line is still the model, the actual, red line is the model, and the orange line is 1 standard deviation shock, right? Meaning it goes the worst. Then at a time point, each time point, I have that variable, I shock it by 1 standard deviation. And the blue line is I shock it by 2 standard deviation, right? So that means correspondingly, your default rate should go higher, right? But actually here, look at this area, is actually around 2008, 2009, is actually going down, right? Supposedly, those curve, the orange line should above red line, and the green line should further above orange line. But there are many different places that is contradicting. So actually, corresponding to this area, it's actually corresponding to the corresponding x, meaning the variable itself, x, is actually this area. So that's why when I shock it, the model goes on the adverse opposite directions. So that's matching the observation here, right? I'm pretty sure if you let your team see their partial dependency plot, there are a lot of local nuances that you will see that something like this. In the local areas, it will fluctuate. But why that fluctuation happen is simply the model trying to capture the local structures of your data. And it turns out it's overfitting, right? At least for these examples. So how we make it an economic models? Because at the end of the day, it's a stress testing model. We want to make sure that the model have economic intuitions, meaning when the drivers go worse, the default rate will go higher, right? So we apply the monotonic constraint, meaning we force the relationship in certain directions. For example, this variable will force that it's monotonically decreasing, right? We can do that in XGBoost. And then it will make intuitive sense, and it can solve the overfitting issue. So now look at the partial dependency, right? Now it's going down always, but it still captures the local structures, right? It's not linear, so it's a straight line, but it has those kind of stages, right? So the backtesting now looks a little bit worse, but that's a trade-off between how you want to apply this constraint or not. Okay. And then the sensitivity analysis now looks much better, at least on level-wise. Is once I shock it, it'll go worse, right? But what else can we find? So the top 2 graphs are without a constraint, the first model. And the bottom 2 graph is actually with constraint. So once we apply the constraint, you can see the difference between PDP. Sorry. And then you can see the sensitivity analysis. But what else can we find, right? So if you look at this area, for other area, there are differentiation between the green line, orange line, red line, and the blue line. But at this area, you see the blue line, red line, and orange line, actually, they're the same. Meaning, when we shock it, it did not go higher. It stayed at that level. And that's why it's going to this issue is interpolation or extrapolation. Because it's tree-based models, if you look at the tree, simple 2 features and the results, we can build a tree for that, right, to decide where it goes. But tree-based method, typically they're good at interpolation, but not extrapolation. Think about if there's another feature, that feature 1 is equal to 2, meaning here this column is 2. Feature 2 is still 1, but the result is 0.5. Right? That's another observation that you never see in a sample, but you see in when you're trying to use this model. So that will end up based on this tree going to 0. So you have misclassifications, right? So that going to the conclusion is this tree-based method doesn't like regression or neurals that is able to extend the predictions infinitely. Once it's going to the end node of the tree, it stays there. Doesn't matter how shock your variables going in, you will get the same results. Right? So this is going to that why we want Ensemble those two methods. Right? We have the first model, sequential GRM, which is more traditional, right? And then we have the GBM, which is gradient boosting machine, which is more advanced. We saw that those two models actually kind of complement each other. So one is more global model, right? If you think about sequential GRM, it does not really capture the local structures. It's more applied on the entire portfolio, right? Even we have some interaction terms. While GBM is more local, it captures all those local nuances, even with those constraints. And one is simpler, one is complex. One can extrapolate, another cannot extrapolate. So then the weights we need, so once we go into stress testing, the scenario we never see in our model development, that we want to make sure that there is an appropriate response from the framework to those scenarios, especially when the scenario is out of historical range. Right. So we simply just put a 50-50% of the weights between those two, right? And for already seen scenarios, we put a 50-50%, we combine those two. For those scenarios we never seen, then we put a sequential, meaning it can extrapolate. So this is how the model, the final model perform looks like. For sure, gradient boosting, even with constraint, it has a lift Gini about 10%, right, out of a traditional method. And then you look at the combination of those two in back testing. So the red line is actually the combination of those two by 50% weight, equal weights of the gradient boosting, which is black line, and the green line is the sequential. So the red line is actually, it tracks the actual default rate pretty well. Right. And then now we go to another paradigm of term structure construction. Once we have those two ensemble models, we can predict the probability of default at a segmentation level, right? But there's one important driver that we use to, in those models is a customer risk rating. And why that's important is simply, this is assessed by our loan officer, right? So meaning they take into consideration a lot of quantitative and qualitative perspectives and assign those ratings to the corporate customers. So it is one of the most important drivers to differentiate the risk, right? You think about a classification question, problems, it's essentially you're trying to, differentiate your good and the bad, right? So the CCAR, which is stands for customer risk rating, does that automatically, right? Unless your internal risk system breaks, right? You supposedly, you have a higher rating, you have lower default risk, and you have lower rating, you have a higher default risk. So that's the one of the most important driver which we saw in the different modelings. And the second is this CCAR change over time, meaning they're not stay the same. However, in the stress testing, when we talk about the future, there's no future CCARs, right? No, the Fed won't generate the future CCAR for us. So we have to forecast it, right? So how are we going to do it? We look at the rate transition matrix, so rating migrations. So for example, to rate this table, these are the ratings, bucket, AAA, AA, all the way to default, right? And then this is, as of today, the rating. This is as of next year, how the rating looks like. Because then there is a rating migration. So we can see, okay, for today, AAA, there are about 90% stay AAA next year, but it migrated to other ratings. And for example, CCC, about 56% stay in CCC next year, but there are about 29% default, right? There are different ways to look at a transition matrix. So this is a long-run average, meaning it across 1981 to 2013, how the rating migration looks like in average, right? And then this is one specific year that how the rating migration looks like. For example, this one is downturn, right? Dot-com bubble. So you would see CCC, other than in the long-run average, we have about 29% that are default. Actually, here, CCC, there are about 50% default. So you can see the transition matrix actually showing a worse than long-run average. Right? So this is something that we want to incorporate. Because think about it, the models we predicted, we constructed, the Ensemble model, only predict this column. Right? We only predict, okay, given the credit rating, given the scenarios, what's the default rate looks like. Right? But we don't have the entire matrix. So to construct the term structure, then we essentially, those are a bunch of mathematics that we construct called systematic factors that capture the shifting between your long-run average default risk and your point-in-time PD, right? If the point-in-time PD is higher, that means your entire transition matrix will be more severe than like the previous example, right? For example, in this specific quarter, that this transition matrix is actually more severe than the long-run average. So then we construct this indicator, and then we construct the transition matrix on the point in time, and find the cumulative transition matrix, get the cumulative default rate, and then get the marginal default rate. So this is some math involved, but it's not rocket science. Okay, so going to the last slide, lessons and learns. So still quote Neil Bremen. So if you know him, he's the one who invented bagging, right? It's the foundation of random forest. So there are two cultures in use of statistical modelings, right? Parametric and non-parametric. There are pros and the cons, right? So here we actually used one of them. We used one from each of those methods, and then we assembled them. We think this will kind of complement the pros and the cons. But in general, I think machine learning is not the cure-all solutions, as you can see from this exercise. But it certainly helps. Right? It captures those nonlinear relationships under certain circumstances. Right? But lesson learned that from this is, for all those machine learning models, it does continuously minimize the errors or the loss functions that you predefined. And many times, it will overemphasize the local structures, like you saw that partial dependency plot, and then cause overfitting. And guarantee you that in the machine learning model you build, you go back to look at them, you will find a lot of local nuances happened. And the second is the interpretability. So how you're going to interpret those models is really key, right? To understand how the model works. But this can partially be addressed. Now there's a lot of interpret tools and a method that are to help us to understand how those machine learning model works. And the last one is extrapolation on the unseen scenarios. It is simply, when we build those models, we have those sample, model performs good. But when we apply those models to the scenarios we've never seen before, how the model will react. So do a lot of tests, scenario test. So from stress testing, it's kind of mimicking what we have, right? For example, in your stock market, you don't know tomorrow's market. What if it crash? What if it crash in a way that we've never seen before, right? How your own model will react to that. It's beneficial that we can run a different test to see the model's performance under those scenarios will definitely help. At least you know that your model's weakness and the strengths, right? And to further enhance it. So that concludes my presentation. Any questions?
Hey, so when you submit these numbers, do you actually use a machine learning model to submit the numbers for baseline fed and for the baseline adverse and severely adverse? Because in some cases, you may actually have the same number for all the three scenarios. So do you see any pushback from the Fed if you are submitting those numbers? If you use the machine learning model?
Yeah, this approach is used as the challenger or benchmark purpose. Our champion model is still using traditional method.
Okay.
Yeah.
Okay, I have one more question. So,
Sure.
So the example that you gave was to predict the find out the probability of default, and you may have like a few like different underliers, and you may have like a monotonic relationship between the underliers and the outcome. But in some cases, if you have like exotic derivatives, you may not have a monotonic relationship. So in those cases, how would you actually put a constraint? So like, for example, you could have like a barrier option, or you could have like a butterfly spread or something like that. And as the underlier is moving, you may probably like, it may be monotonic for some time, and after that, it may just like drop, or it may not be non-monotonic. So how would you apply the constraints?
Yeah, so for that, I believe that you would segregate your training data set, or based on your judgment, into those areas, and then apply it, correspondingly. Because I know that for this one, it's economic drivers. You're supposed to apply, across the board. But in that cases, if you have naturally you have a quadratic relationship, right? You could cut at the middle and apply on the both ends, right? So still, you should be able to capture some of the local structures that are using those ways.
Thank you, Ying. Very impressive presentation. I had a question about how to explain the model, given that it's a weak sample of like two different approach. So for linear regression, you can simply look at the coefficients. For the machine learning, it might be a little bit black box, but you have like strategies to get to the predictive part of it, and then how to explain it. But then once you assemble those two, do you look at each model individually, or if you look at it like as a whole package, how do you think about offsetting impacts and how to explain to regulators?
Yeah, we did look at, thanks for the question. So we did look at them combined together, right? There are other kind of testing we did, like a variable contribution, right, from the ensemble of those two approaches. Also the sensitivity analysis, we also did on a combined basis. So once we combine them, we want to test them as a whole.
So I had a question on the. Can you hear me?
Yeah,
Okay.
I can hear.
So I had a question on the ensemble, the 50-50. So I see that it can have a stabilizing effect, but was there any concern that by doing that, since the gradient boosting is more of an interpolator, that it could actually dampen the effect of the scenario, or dampen an effect that was legitimate?
Yeah, actually, thanks for the question. So in the unseen scenarios, it's actually 100 and 0. So in unseen scenarios, we switch entirely to the traditional model while not using gradient boosting. But in the same scenario, meaning inside the scenario that we saw before, we do 50-50. Yeah.
I got two questions. So the first one, you have a regression problem, right? So your y is numerical.
Yeah.
How can logistic regression do regression? So you said one of your algorithm is logistic regression, right?
Right.
How can logistic regression give numerical value, numerical output?
This is a classification question.
Oh,
So
really? Okay.
the historical is whether this is corporate default or not. So 0 and 1.
Oh, just 0 and 1.
Yeah, 0 and 1.
Oh, I got
But the
you,
output probability.
Okay. Okay, my second question is, so instead of doing 50-50, like just issue them with manual weights, have you considered including more models and then building a like a more sophisticated ensemble, so you can give each model their own coefficient and then combine them all? And so because you mentioned that you also did other models like including A and N, and why don't you just bring them all in and then just let the model tells you what coefficient you can assign to all of those models instead of just fix them down to 50-50, because maybe for the other problem 50-50 is not the best choice, or 0-100 is not the best choice.
Yeah, absolutely. So I think 50-50 is for simple purpose. First, we want to take this step forward, and then later on, if this one is accepted, then we could do some optimization to find the optimal weights, right? So indeed, the 50-50 is just for simple, it's kind of a way, because we treat them equally. And back to the ANN case, that we did find out the ANN, the extrapolation of artificial, for neural nets, doesn't matter is ANN or RNN, is it also have extrapolation issues. Because once it's going to those unseen scenarios, you don't know how those relationship holds, right? All the weights attached to those nodes or layers. It might be go dramatically that it's like a game, right? So, but I believe there recently there's a paper published by Google DeepMind that they're trying to kind of solving the problem of the extrapolation of neural nets. Yep.
Hi, thank you so much for the presentation. I have two questions. One is that you mentioned that this is currently a challenger model, which means that it hasn't been used for the official CCAR testing. But has the regulator give you any feedback? And then also, do you anticipate in the next round you start to applying these machine learning-based models to replace the sort of traditional model? So that's my first question. And the second question is like, what's the motivation to apply a machine learning model in the stress testing space? Because it's my own perspective that stress testing is not necessarily the areas that needs the most accurate results. There are many reasons of that. One of it is that it's very hard to verify, although we do out of sample testing all the testings, but really what matters of that non-quarter forecast is something you can never do a back testing, right? So lots of places people take that stress testing is an exercise just to be reasonably stress my profile, not necessarily needs to seek the most accuracy. And so I'm just very interested in what's the motivation of applying machine learning algorithms in the stress testing.
Yeah, thanks. Thanks for the question. So first is I think nowadays that both regulator or banks are trying to see if those methodologies can be applied, right? So those are those testing that we perform, right? So also regulator is continuing learning that whether those things can be applied, right? So there will be kind of a mutual learning process. The second question is about what's the motivation to apply this? So accuracy is definitely, because used to a lot of emphasis on conservatism for stress testing purpose. But I believe that has been shifted to you want to have more accurate estimation, because later on, stress testing, CISO, IFRS 9, those will be kind of merged in some sense. Then you would want to have some accurate estimate rather than you only just put it more conservatively.
Thank you.
So, just out of my curiosity, when you say unseen scenario, do you mean the unseen data point for that principal component one or unseen of all the combination of the macroeconomic variable forecast?
Unseen of all microeconomic variables.
Okay, so I assume most of the combination will be unseen, right? Because
It's actually, so specifically that 1 or 2 quarters is unseen. So if you look at this, so only this quarter and this quarter, probably those 2 quarters, the most severe quarters, is unseen because all those has seen before, right?
okay, so in that combination of macroeconomic variable, as long as that data point exists before in a single macroeconomic variable,
Yep,
that means it's seen, right? Even though the combination may be unseen.
right.
Okay, got
Yeah.
it. Thanks.
So unseen means goes to out of the range of.
Yeah, out of range of in-sample scenarios you see, yeah. Thank you very much.
Thank you very much to Yoon. And we have a half-hour break, so we'll be right back here at 4:30 for our last speaker. Thank you.